You are looking at the most distant object the human eye has ever witnessed. To the astronomers who found it, it wasn't just a discovery, it was a crisis wrapped in a pixel. They call it MOM-Z14, the mother of miracles. And for 13.5 billion years, its light has been screaming across the expanding fabric of space-time, getting stretched and reddened until those ancient photons finally died against the gold-plated mirrors of the James Webb Space Telescope. But as the data trickled into the labs at MIT and NASA, the excitement didn't lead to a celebration. It led to a silence. Because according to every model we have of how the universe began, this galaxy shouldn't be a miracle. It should be an impossibility. To understand why astronomers are losing sleep, you have to understand the timeline. If the entire history of the universe were a single calendar year, the Big Bang happened on the first second of January 1st. Modern humans didn't even show up until the final 10 minutes of December 31st. We've always believed that the first few days of that cosmic January were dark, quiet and empty, a period called the Cosmic Dark Ages. We expected the first galaxies to be like fragile, primitive nurseries, small, dim collections of pure hydrogen and helium, slowly pulling themselves together in the cold dark. But when Webb peaked into the first week of January, specifically just 280 million years after the Big Bang, it didn't find a nursery. It found an adolescent with the lungs of a grown man. This is the adolescent in the nursery paradox, a medical mystery on a universal scale. When we look at MOM-Z14, we aren't just seeing a record breaker at a redshift of 14.44. We are looking at a galaxy that is compact, extraordinarily luminous, and most troublingly, chemically scarred. In a galaxy that is supposedly only 280 million years old, we are seeing the clear, spectroscopic fingerprints of oxygen and nitrogen. Let that sink in for a moment. Oxygen doesn't just exist at the beginning of time. It isn't a primary ingredient of the Big Bang. Oxygen is the ash of dead stars. It is forged in the nuclear furnaces of massive suns, which must then live their entire lives, exhaust their fuel, and explode as supernovas to scatter those heavy elements back into the void. Only then can a new generation of stars breathe in that enriched gas. To find significant amounts of oxygen in MOM-Z14 is like walking into a delivery room and finding a newborn baby who already has the lungs of a 30-year-old. It implies a stellar metabolism, so fast, so aggressive, that it defies our understanding of cosmic time. Before Webb, we thought the early universe moved with a certain sluggish grace. We believed it took billions of years for galaxies to build up the heavy elements required for complexity. But the Mother of Miracles is telling us that the cosmic dawn wasn't a slow sunrise. It was a flash fire. The data shows that this tiny object, only a few hundred light years across compared to our Milky Way's 100,000, is punching so far above its weight class that it's nearly 100 times brighter than our most advanced simulations predicted. It's as if the early universe was operating under a different set of metabolic rules, converting gas into stars with a terrifying, frantic efficiency that we never saw coming. When the first papers on MOM-Z14 were circulated as preprints, the reaction from the scientific community was one of profound astrophysics under stress. Kevin Heinlein, one of the lead researchers on the JADES team, admitted his first reaction was pure skepticism. He thought the telescope had fooled us. He hoped it was a little red dot, a deceptive object where a hidden black hole mimics the light of a mature galaxy. But as the spectroscopic analysis came back, the mystery only deepened. There was no sign of a feeding supermassive black hole at the center of MOM-Z14. There was no engine to explain the glow. It was just raw, unadulterated star power. This is where the lore gets even weirder, and it's something most documentaries won't tell you. The chemical signatures we see in this impossible galaxy, 13 billion light years away, aren't just abstract data points, they're eerily familiar. They match the specific nitrogen ratios we find in the oldest fossils in our own neighbourhood, the globular clusters orbiting the Milky Way. This creates a haunting bridge across time. It suggests that the very first fires of the universe didn't just happen out there at the edge of the abyss. They left their fingerprints right here in our own backyard. The farthest thing we can see and the oldest things we can touch are telling the same story. The beginning was much busier, much faster, and much more violent than we ever dared to imagine. This isn't a simple case of the Big Bang is wrong, despite what you might see on a sensationalist Facebook headline. It's something far more interesting. It's a collision between reality and our imagination. We built our models based on a universe that grows up slowly and logically. But Webb has shown us a universe that was born running. The stellar metabolism of MOM-Z14 suggests that the first stars weren't the stable, long-lived suns we see today. They may have been monsters of the first fire, monstrous, short-lived firecrackers that lived and died in a heartbeat, saturating the early universe with heavy elements before the first 300 million years were even up. But as the headlines began to mutate across Reddit and the wider internet, the scientific nuance started to dissolve into something else. In the vacuum of certainty created by this impossible galaxy, fringe theories began to rush in. People started asking if the universe is effectively older than we think, or if we are misreading the clocks of space-time entirely. Some even began to suggest that the reason these galaxies look so mature so early is because they didn't start from zero, that they are the remnants of something that existed before the Big Bang, or perhaps fingerprints of a universe born inside a black hole. We are currently standing at the edge of what we call visible time. Every time we push that redshift number higher, from 13 to 14 and soon to 15, we aren't just looking further away, we are looking at a version of our history that is becoming increasingly illegible. MOM-Z14 is a warning. It is telling us that our baby pictures of the cosmos are actually the portraits of a complex, sophisticated teenager. And if we can't explain how a galaxy grew that much skin and bone in just 280 million years, then we have to admit that we don't just have a problem with our telescopes. We have a problem with our story. The trial of our standard model has begun, and the Mother of Miracles is the first witness for the prosecution. She is small, she is red, and she is brilliant. And she is asking us one simple, terrifying question. Do we actually know how old we are? As we dig deeper into the chemical crime scene of this galaxy, we're finding that the answers don't just lie in the distant past, they lie in the very mechanics of how light, matter, and time itself collided to create the world we see today. This is the mystery of the impossible baby. And to solve it, we're going to have to look at the monsters that were hiding in the dark before the first light even broke. To understand the crisis currently unfolding in the backrooms of astrophysics departments, we first have to talk about the wall. In astronomy, we don't just look across distance, we look across time. Every photon that hits a telescope lens is a messenger from the past, but for decades we've been staring at a thick, impenetrable veil that separates the universe we know from the universe that was. We call this the redshift wall, and for a long time we thought it was the absolute limit of what the human eye could ever hope to witness. Imagine you're trying to read a book, but the first 50 pages have been glued together and soaked in ink. That is what the early universe looks like to a standard telescope. For the first few 100 million years after the Big Bang, the cosmos was a place of absolute, suffocating darkness. There were no stars, there were no galaxies, there was only a hot, dense, neutral soup of hydrogen and helium gas. Cosmologists call this the cosmic dark ages. It wasn't just dark because there was nothing to see. It was dark because the universe itself was opaque. It was a primordial fog so thick that even if a light had turned on, those photons wouldn't have been able to travel more than a few inches before being swallowed by the mist. This fog began to lift during a violent, transformative era known as the Cosmic Dawn. This was the moment the first stars ignited, their intense ultraviolet radiation acting like a cosmic blowtorch, carving out bubbles of clarity in the hydrogen fog. This process, called rhionization, eventually turned the universe transparent, allowing light to finally travel across the abyss. Astronomers have spent their entire careers trying to catch a glimpse of that first light, to see those first bubbles of reality forming. But there was a problem. The universe was expanding, and that expansion was doing something strange to the light. Think of space as a giant rubber band. As the universe expands, it stretches the light travelling through it. If a star emits a high-energy blue photon 13 billion years ago, by the time that photon reaches Earth, the expansion of space has stretched its wavelength so much that it has shifted out of the visible spectrum through the red and deep into the infrared. This is redshift. The further away an object is, the more the rubber band has stretched its light. By the time we get to the very beginning, to the cosmic dawn, the light is so redshifted that it is completely invisible to the human eye and to almost every telescope we had ever built. For years, our champion in this race against time was the Hubble Space Telescope. Hubble was a masterpiece of engineering, but it had a fundamental limit. Its 2.4-meter mirror and its sensitivity were tuned mostly to visible light. It could see pretty far back. It could see the afterglow of the universe's middle age. But as it looked deeper toward the beginning, it started hitting the wall. The light from the first galaxies was simply too red, too stretched for Hubble to catch. But then, in 2016, Hubble did something extraordinary. It spotted a tiny faint smudge of light in the Ursa Major constellation. They named it GNZ11. It was at a redshift of 11.1, meaning we were seeing it as it existed 13.4 billion years ago. For a long time, GNZ11 was the undisputed king of the cosmic Olympics. It sat right at the edge of the wall, a lone sentinel at the limit of Hubble's vision. It was a landmark discovery because it proved that galaxies were already forming just 400 million years after the Big Bang. At the time, we thought GNZ11 was the absolute end of the line. We assumed that anything further back would be too dim, too primitive, or simply non-existent. We were wrong. The entry of the James Webb Space Telescope into the cosmic Olympics didn't just break Hubble's records, it demolished the entire stadium. With its massive 6.5-meter gold-plated mirror and its infrared eyes, Webb was designed specifically to peer over the redshift wall. It was built to find the invisible light that had been travelling since the dawn of time. And as soon as the first data started trickling in, the cosmic Olympics turned into a sprint that no one was prepared for. First came the JADES survey. The James Webb Advanced Deep Extragalactic Survey began hunting for little red dots, objects so redshifted they only appear in the longest infrared wavelengths. Almost immediately, they found JADES-GS-Z14-0. The redshift was 14.32. The crown was snatched from GNZ11. We were now looking at a galaxy as it existed less than 300 million years after the Big Bang. But the record didn't even have time to settle before the mother of miracles appeared. MOM-Z14, confirmed at a redshift of 14.44, pushed the boundary even further, taking us back to just 280 million years after the beginning. But here is the tension that is causing the astrophysics under stress you keep hearing about. In a normal Olympic race, you expect the athletes to get more tired and less capable as the conditions get harder. You expect the galaxies at the very edge of time to be the most primitive, the most fragile, the most unformed. We expected to find baby pictures, tiny chaotic clumps of gas that were just beginning to figure out how to be galaxies. Instead, we found something that looks far too mature. When we look at MOM-Z14 and JADES-GS-Z14-0, we aren't seeing babies. We are seeing galaxies that are 100 times more luminous than our models predicted. They are compact, yes, but they are blazing with the light of millions of stars. They aren't the rare cosmic unicorns we expected to find sparingly across the sky. They are popping up everywhere. The data shows that bright, massive galaxies at this extreme redshift are over 100 times more common than our best supercomputer simulations ever allowed for. This is the maturity paradox. Imagine opening a photo album that is supposed to contain pictures of a newborn on its first day of life. You turn to the first page, and instead of a swaddled infant, you see a photograph of a toddler who is already walking and talking. You don't just say, "Oh, look how fast he grew." You say, "Wait, this photo is impossible. The timing doesn't work." That is the feeling in the astronomical community right now. These galaxies are punching way above their weight class. According to the standard lambda-CDM model, the bedrock of our understanding of the universe, there simply shouldn't have been enough time for gravity to pull that much matter together, for that many stars to ignite, and for that much light to be generated. To see these galaxies so bright and so ready just 280 million years after the Big Bang is like finding a skyscraper in a town that hasn't even finished laying its first roads. The cosmic Olympics has revealed a fundamental mismatch between our theories and our reality. We are peeking at the universe's earliest days, and the babies in the nursery are looking back at us with the eyes of veterans. They are energetically complex, chemically enriched, and far more numerous than we ever dreamed. This has led to a split in the scientific world. On one side, you have the model defenders, who argue that we don't need to throw out the Big Bang just yet. They suggest that maybe we just underestimated how efficient the early universe was. Maybe the first star-forming regions were like high-pressure furnaces, converting gas into stars at a rate we've never seen in the modern universe. Maybe the brightness to mass calculations we've been using for decades are simply naive when applied to the ancient past. They argue that these galaxies aren't too old, they're just too good at making stars. But on the other side, there is a growing group of anomaly hunters. They look at the redshift wall and see something more than just a measurement error. They see a hint that the effective age of the universe might be different than we thought. They look at the little red dots and wonder if we are misreading the clocks of space-time entirely. This is where the fringe starts to bleed into the mainstream. If the standard model says these galaxies shouldn't exist, and yet we are staring right at them, then the problem might not be with the galaxy. The problem might be with the model. As Webb continues to push the record higher, searching for redshift 15, 16 and beyond, the tension only tightens. We are rapidly approaching a point where the adolescent in the nursery won't just be an anomaly, it will be a flat-out contradiction. Every new record breaker is another chisel strike against our long-standing assumptions. We wanted to see the beginning of the story, but it turns out we walked into the theatre after the first act was already over. The redshift wall was supposed to be the end of our journey, but it has turned out to be the start of a much deeper mystery. We are finding that the cosmic dawn was not a slow, gentle awakening. It was a frantic, brilliant, and terrifyingly fast explosion of structure. The baby pictures are far too mature, and as we analyse the light of MOM-Z14 more closely, we're realising that the problem isn't just how much light there is, it's what that light is made of. Because tucked inside those ancient photons is a chemical signature that should have taken billions of years to create, and yet there it is, staring at us from the very beginning of time. To truly understand the panic currently vibrating through the halls of major research universities, you have to look past the pretty pictures. The true drama isn't found in the red smudge of the image itself, but in the barcode of light that defines it. This is the science of spectroscopy, the process of taking the faint, ancient light of a galaxy, like MOM-Z14, and stretching it out into a rainbow of data. To an astronomer, this rainbow is a chemical crime scene, and the evidence left behind is telling a story that defies the laws of cosmic inheritance. When the team at MIT's Kavli Institute first dissected the light of MOM-Z14 using the NIR SPEC instrument on the Webb telescope, they weren't just looking for distance, they were looking for the ingredients. In a universe that is only 280 million years old, you expect to find a pristine environment. You expect a galaxy made of the clean stuff, hydrogen and helium, the only elements forged in the Big Bang. But when the spectral lines began to appear on their monitors, they saw something impossible. They saw the clear, undeniable signatures of oxygen and nitrogen. This is where the medical mystery of the early universe becomes a full-blown paradox. Oxygen and nitrogen are not natural to the young universe. They are heavy elements, what astronomers call metals. These elements are only forged in the nuclear hearts of stars. For oxygen to exist in such high quantities in MOM-Z14, stars had to be born. They had to live their entire lives. They had to exhaust their fuel, and they had to die in massive supernova explosions to seed the surrounding gas with their metallic ash. Only then could the next generation of stars be born from that enriched gas. But here is the problem. The universe was only 280 million years old when this light was emitted. In our modern neighbourhood, stars like our Sun take billions of years to evolve. Even massive stars live for tens of millions of years. For MOM-Z14 to be as chemically scarred as the data shows, it implies that multiple generations of massive stars had already lived and died before the universe was even 2% of its current age. It is the cosmic equivalent of finding a bustling industrial metropolis in a land that was supposed to be a primitive, untouched wilderness. The mystery deepened when the team analysed the specific ratio of nitrogen to oxygen. In the modern universe, nitrogen is produced relatively slowly in the outer layers of stars. Yet in this baby galaxy, the nitrogen levels were unexpectedly high, higher than almost any model predicted. It wasn't just that the galaxy was dirty with heavy elements, it was that the pollution was far too sophisticated. This isn't just a galaxy, it's a factory that has been running at 1000% capacity since the first second of time. The question every astronomer is asking is, how? How do you get from a universe of pure hydrogen to a chemically complex, oxygen-breathing galaxy in the time it takes for a single, massive star to flicker? This spectroscopic crime scene suggests that the stellar metabolism of the early universe was operating on a different clock entirely. We are looking at a system that processed its gas with a violent, frantic efficiency that we didn't think was physically possible. We aren't just missing a few details, we are missing a fundamental chapter in the history of how matter itself evolved. In the modern universe, whenever we see a tiny galaxy glowing with the brilliance of 1,000 suns, we think we know the culprit. We look for the engine. Astronomers call this an active galactic nucleus, but to the rest of the world, they are known as quasars. These are the most powerful objects in the cosmos. Beacons of light so intense they can outshine their entire host galaxy from halfway across the universe. But that light isn't coming from stars, it's coming from a monster, a supermassive black hole at the very centre, feasting on surrounding gas and dust at such a violent rate that the friction and heat generate a blaze of light that screams across the void. For a long time, this was our shortcut to explaining how a very young galaxy could look so bright. We assumed that if we found something luminous in the early universe, we were just seeing a massive black hole that had grown out of a gigantic seed at an unprecedented rate. It was a comfortable explanation because it meant the galaxy itself didn't have to be mature. It just needed a hungry heart. But as the data from the James Webb Space Telescope began to fill the monitors in labs from MIT to Santa Cruz, the comfort of that explanation evaporated. The heart was missing. When the teams behind JADES-GS-Z14-0 and the mother of miracles, MOM-Z14, first saw how bright these objects were, their first instinct was to look for the engine. They were searching for what astronomers call little red dots, mysterious compact objects, where a hidden feeding black hole mimics the light of a massive collection of stars. If a black hole was doing the heavy lifting, our models of galaxy formation would stay intact. We wouldn't have to explain how millions of stars formed in a heartbeat. We'd just have to explain how one black hole got very fat, very fast. Yet as the spectroscopic analysis came back, the mystery took a sharp, uncomfortable turn. In a feeding black hole, you expect to see specific high-energy emission lines, the flag of a ship in a storm. You expect the light to be concentrated in a single sharp point at the center. But in JADES-GS-Z14-0 and MOM-Z14, the light is extended. It isn't a single point, it's spread out across the body of the galaxy. There is no sign of a supermassive black hole regulating the pace of star birth or driving the growth of the system. These galaxies are punching above their weight class purely through raw, unadulterated star power. This is the anomaly of the naked giant. To produce the amount of light Webb is seeing without the help of a black hole, these tiny galaxies, some just 500 light-years across compared to the Milky Way's 100,000, must be forming stars at a rate that defies logic. To put this in perspective, our own Milky Way is a massive, mature galaxy that produces maybe 1 or 2 new stars every year. For MOM-Z14 to be this bright, it would need to be cranking out stars like a factory, potentially producing 100 new suns every single year. Imagine a city the size of a small, rural village suddenly generating the electrical power of a global superpower like the United States. You would look for the massive power plant hidden in the hills, but when you look at these galaxies, there is no plant. There is no central engine. There is only the frantic collective glow of the citizens themselves. This Herculean starburst phase is a moment in galactic evolution that we thought we understood. But seeing it happen 280 million years after the Big Bang changes everything. It means that the early universe didn't need black holes to create brilliance. It was capable of igniting tens of millions of stars simultaneously in a compact volume of space with an efficiency we've never seen in the modern world. The problem here is a double-edged sword that cuts through every existing model of cosmic history. If these galaxies did have supermassive black holes, we would have a growth crisis. To reach the required mass to explain this much light, a black hole would have to be 100 million times more massive than our Sun just 300 million years after the Big Bang. That's a growth rate that challenges the very laws of physics, specifically the Eddington limit, which dictates how fast a black hole can eat before its own radiation pushes its food away. But because Webb doesn't see the black hole, we are left with a starburst crisis. We have to explain how gravity pulled enough gas into such a tiny space to ignite a firework display of millions of stars in a window of time. That is, quite frankly, too short for the gas to have even cooled down. This missing heart is why astronomers are using phrases like astrophysics under stress. It's not just that the galaxies are there, it's that they are doing the impossible without the one tool we thought they needed. In the modern universe, supermassive black holes act as regulators. They are the governors of a galaxy's metabolism, blowing out gas and slowing down star formation, so the galaxy doesn't burn itself out. But MOM-Z14 and its siblings are unregulated. They are naked giants, burning through their fuel with a terrifying, frantic energy. This forces us to ask a question that borders on the philosophical. Why was the early universe so much more efficient at making light than the universe we live in today? Why was the cosmic dawn a place where stars could ignite in massive, dense clusters almost immediately, while today it takes millions of years for a single nebula to collapse? Some researchers are beginning to suspect that we've been looking at the brightness to mass translation all wrong. Maybe these galaxies aren't actually as heavy as they look. Maybe they're just incredibly good at pretending to be big. But the chemical evidence we discussed in the last chapter, the oxygen and the nitrogen, suggests they aren't pretending. Those elements are physical ash. They prove that stars have already lived and died. So if there is no black hole engine to explain the glow, and the galaxy is already dirty with the chemicals of dead stars, we are left with only one conclusion. The first stars weren't like our sun. They weren't stable, long-lived points of light. They were something else entirely. By removing the black hole from the equation, Webb has stripped away our easiest excuse. We are now forced to confront the raw physics of the first light. We are looking at a universe that was born running, a place where the rules of star birth were so different and so much more aggressive that it makes our modern cosmos look like a graveyard in comparison. If the heart is missing, then the skin and the bone of these galaxies must be doing something we never thought possible. And to find out what that is, we have to look at the monsters that were hiding in the nursery. Stars so massive and so violent that they didn't just light up the dark. They rewrote the periodic table in a heartbeat. If it isn't a black hole doing the work, and if there is no central engine to explain the blinding brilliance of a galaxy like MOM-Z14, we are forced to look at the stars themselves. But we have to look at them through a different lens, because the stars we see when we look out of our windows tonight, the stable yellow suns and the small cool red dwarfs, are not the stars that built the beginning of time. To solve the mystery of the adolescent in the nursery, astronomers are pivoting toward a theory that sounds less like a textbook and more like a legend from a lost age. They call it the top-heavy initial mass function, or the top-heavy IMF, but in the quiet, late-night conversations between researchers, they call them something else, the monsters of the first fire. To understand why this theory is a game-changer, you have to understand how a galaxy usually decides what kind of stars to make. In our modern universe, star formation follows a very predictable recipe. For every one massive, bright blue giant the universe creates, it bakes hundreds of tiny, dim, long-lived red dwarfs. It's a bottom-heavy system, mostly small stuff, with a few big stars scattered in like rare jewels. But the top-heavy theory suggests that in the high-pressure, hyper-dense environment of the early universe, the recipe was completely flipped. In those first few 100 million years, the universe didn't bother with the small stuff. It didn't make cupcakes, it only made giant wedding cakes. It favoured the creation of monstrous, supermassive stars on a scale we simply don't see today. Imagine a star that is not just twice or 10 times the mass of our Sun, but 300 times more massive. Imagine a star so hot that it doesn't glow yellow or even white, but a fierce, violent ultraviolet blue. These are the population 3 stars, the first generation. They were born from the pristine, untouched hydrogen and helium of the Big Bang, and because they lacked any heavy elements to help them cool down, as they collapsed, they grew to gargantuan proportions. These were the monsters that inhabited the first galaxies, and their existence would explain exactly why Webb is seeing galaxies that are 100 times brighter than our simulations ever allowed for. We weren't overestimating the size of the galaxies. We were underestimating the star power of the individuals. But being a monster comes with a terrible price. In the world of stellar physics, the bigger you are, the faster you die. While our Sun is a slow-burning candle that will last for 10 billion years, these first-generation monsters were like sticks of dynamite. They lived with a frantic, desperate intensity. A star 300 times the mass of the Sun might live for only 2 or 3 million years. In cosmic terms, that is a heartbeat. It is a flicker in the dark. But it is what happens when that flicker ends that solves the chemical mystery of MOM-Z14. This is the concept of chemical fireworks. When these monstrous stars exhausted their fuel, they didn't just fade away. They exploded with a violence that is almost impossible to wrap the human mind around. These weren't standard supernovas. They were hypernovas, ripping the fabric of their local environment apart and screaming heavy elements into the void. This is the stellar metabolism we've been looking for, because these monsters lived and died so quickly they could act as a rapid response team for the periodic table. They could take a universe of pure, boring hydrogen and saturate it with oxygen, nitrogen, and carbon in just a few million years. When Webb looks at MOM-Z14 and sees oxygen in its lungs, this is the mechanism at work. We don't need billions of years of slow, patient evolution if the first generation of stars was made of these short-lived monsters. They could have gone through 5 or 10 entire generations of birth and death before the universe was even 300 million years old. They were the ultimate chemical recyclers, turning the primordial soup into a complex, enriched environment at a speed that makes our modern universe look like it's standing still. Visually, the cosmic dawn wasn't a soft, gradual awakening. If this theory is correct, it was a terrifying, brilliant battlefield. You wouldn't see the calm, majestic spirals of the modern era. You would see small, compact clumps of gas, only a fraction of the size of the Milky Way, blazing with the light of millions of these violet-blue monsters. You would see constant flashes of light as these giants detonated, one after another, like a grand finale of a fireworks show that never ends. Each explosion would send shockwaves through the surrounding gas, triggering the birth of the next generation of stars, even as it poisoned the nursery with the heavy elements needed for complexity. This theory allows the Big Bang to stay intact, but it demands that we admit our simulations were naive. We built our models of the early universe based on the slow and steady rules we see around us today. We didn't account for the desperation of the beginning. Webb has shown us that the early universe was far more efficient, far more active, and far more violent than we ever dared to imagine. It tells us that the maturity paradox isn't a problem with the age of the universe, but a testament to the sheer power of the first stars. But this raises a haunting question for the stellar archaeologists. If the early universe was filled with these monsters, and if they lived and died in the blink of an eye, did they leave anything behind that we can still touch? Or are they just ghosts, long gone before the first light even reached our neighborhood? To answer that, we don't have to look 13 billion light years away. We just have to look at the fossils hiding in the outskirts of our own Milky Way. Because it turns out the monsters of the first fire might have left their fingerprints much closer to home than we ever expected, in the ancient, tightly packed clusters that have been orbiting us since the very beginning. The story of MOM-Z14 isn't just about a distant record breaker, it's about a different kind of reality. A high-energy, high-pressure era where the rules of life and death were compressed into a frantic sprint. We are finding that the impossible brightness of the dawn wasn't a mistake. It was the result of a generation of stars that was built to burn bright and die fast, leaving behind a universe that was adolescent almost as soon as it was born. And as we dig into the chemistry of these monsters, we're realizing that they didn't just light up the dark. They prepared the stage for everything that came after, including us. The monstrous first stars feels like it's happening at the edge of a different universe. It is easy to treat a galaxy like MOM-Z14 as a distant freak of nature, a spectral ghost haunting the abyss 13.5 billion light-years away. But the true shock of this discovery isn't just how far away it is, it's how close it feels. To understand the deepest mystery of the Mother of Miracles, we have to stop looking at the edge of the cosmos and start looking at our own backyard. We have to pivot from deep space exploration to something astronomers call stellar archaeology. Because it turns out the impossible chemistry of the first galaxies isn't just a distant data point, It's a mirror reflecting the oldest fossils in our own Milky Way. Imagine walking through the outskirts of our galaxy and stumbling upon a graveyard of stars that has been there since the beginning of time. These are the globular clusters, ancient, tightly packed spheres of hundreds of thousands of stars, held together by their own gravity, orbiting the Milky Way like silent, glittering sentinels. For decades, these clusters have been the oldest stellar structures we know of, but they have also been one of our biggest headaches. When we look at their chemistry, they don't look like the rest of the galaxy. They contain a specific, weird chemical signature, an unexpectedly high ratio of nitrogen relative to carbon. For a long time, we didn't know where that nitrogen came from. We assumed these clusters were born in the first few billion years of cosmic history, slowly building up their complexity over eons. We thought they were the product of a long, patient evolution, but then the James Webb Space Telescope pointed its infrared eyes at MOM-Z14 and dissected its light into a spectrum. When the data from 280 million years after the Big Bang came back, the team at MIT's Kavli Institute saw something that made their blood run cold. They found the exact same chemical fingerprint, that unusually high ratio of nitrogen. This is the smoking gun of stellar archaeology. The chemical scar we see in the farthest galaxy ever observed is eerily familiar because it is the same scar we see in the oldest stars orbiting our own sun. This realization rewrites the entire timeline of our own origin story. Before this discovery, we assumed that the dense, high-pressure environments needed to forge this kind of nitrogen ratio took a long time to develop. We thought the Milky Way's globular clusters were the grandchildren of the first stars, but MOM-Z14 proves that this chemistry was already happening almost immediately after the universe became transparent. It means that the fossils of the first fire we see in our own neighborhood aren't just old, they are the direct survivors of the era Webb is currently witnessing. The furthest thing we can see and the oldest things we can touch are telling the exact same story across 13 billion years. This creates a bridge across time that most documentaries completely ignore. We aren't just observing a record breaker, we are observing our ancestors in the middle of their birth pangs. It suggests that the miracle of MOM-Z14 wasn't a local anomaly at the edge of the universe. It was the universal standard for how the first structures were built. Those monstrous stars we talked about, the ones that lived fast and died hard, weren't just out there in the distance. They were here too. They were the architects of the globular clusters that still orbit us today. They were the ones who saturated the early universe with nitrogen and oxygen with such frantic efficiency that it looks impossible to our modern, slower models. Think about what that means for our understanding of the Milky Way. It implies that our galaxy didn't just slowly coalesce from a gentle cloud of gas. It was seeded by the same violent, brilliant, and hyperactive processes we see in MOM-Z14. Our own galactic home was born in a flashfire of star power, governed by a stellar metabolism that was 100 times faster than anything we see today. We used to think of the early universe as a quiet nursery, but the local connection tells us it was a high-octane factory, and the globular clusters are the heavy machinery that survived the explosion. This archaeological perspective changes the way we view the Webb's data. Every time we find a new little red dot or a high redshift galaxy that is too chemically evolved, we aren't just breaking records. We are finding missing chapters in our own biography. We are realizing that the adolescent in the nursery is us. The reason MOM-Z14 looks so mature is that it had to be mature to eventually become the foundation for everything that followed. The miracle is that we can see the beginning of the very chain of events that led to the heavy elements in our own blood and the ancient stars in our own sky. By connecting the farthest object to the local relic, We eliminate the distance that makes astronomy feel abstract. We are looking at a mirror. The nitrogen anomaly in our globular clusters was a message from the beginning of time that we couldn't read until Webb gave us the cipher. Now that we have it, we can see that the universe was built different from day one. It didn't take its time. It didn't wait for billions of years to become complex. It hit the ground running, forging the seeds of our own galaxy in a frantic burst of creativity that we are only now beginning to map. But as we solve the mystery of where the nitrogen came from, a more seductive and dangerous question starts to emerge. If the beginning was this busy, if the universe was this ready, and this structured just 280 million years after the Big Bang, then was it really a beginning at all? When the data outruns our intuition this badly, humans naturally reach for even more radical stories to fill the void. And that brings us to the most controversial chapter in the trial of the Standard Model. The idea that the reason the beginning looks so finished is that it wasn't an explosion from nothing, but a rebirth from inside something else. We are entering the territory of the seductive red herring, where the physics of the abyss starts to suggest that we might be living inside a ghost. When the data outruns our intuition, and the universe we see through our telescopes refuses to match the universe we've written into our textbooks, a very specific kind of silence settles over the scientific community. It is the silence of a vacuum, and in the world of human storytelling, a vacuum of certainty is never empty for long. When the Standard Model of cosmology feels like it is under an unbearable amount of stress, we naturally reach for the most radical, most cinematic explanations we can find to fill the void. This is the era of the seductive red herring, a moment where physics stops being merely a record of history and starts becoming a new kind of myth. And the most tempting myth of all is the idea that the reason the beginning of the universe looks so finished and so complex is that it wasn't actually a beginning at all. Instead, it might have been a rebirth from inside the heart of a monster. This is the core of Schwarzschild cosmology, often playfully or terrifyingly called the black hole universe theory. It proposes a reality that sounds like pure science fiction, that our entire observable universe, from the farthest reach of MOM-Z14 to the atoms in your own hand, exists inside the event horizon of a supermassive black hole belonging to a much larger, much older parent universe. In this framework, the Big Bang was not an explosion that happened in empty space. It was the exact moment matter collapsed in that parent universe to form a black hole, creating a new, self-contained space-time inside its boundary. It is a vision of reality as a set of cosmic Russian dolls, where every black hole we see in our own sky, at the center of the Milky Way, or at the heart of a distant quasar, is actually a doorway spawning its own baby universe on the other side. The reason this theory has suddenly moved from the fringe of Reddit threads into the mainstream of public fascination is that it offers a seductive escape hatch for the problems Webb has uncovered. If our universe was born inside a black hole, the clock of history doesn't necessarily start at zero. We wouldn't be starting from a perfectly smooth, simple state. We would be starting with residual structure, seeds of matter and information inherited from the parent universe. This would explain why galaxies like MOM-Z14 look like adolescents only 280 million years after the Big Bang. They didn't have to grow up from nothing because the genetic material for structure was already there. But the temptation of this theory isn't just based on a feeling. It points to a very specific, very strange piece of evidence: the way galaxies spin. In a truly random, isotropic universe born from a simple explosion, you would expect galaxy rotations to be evenly split, 50% spinning clockwise and 50% spinning counterclockwise. However, recent studies of large-scale cosmic structures have found a troubling asymmetry. An oddly high number of galaxies appear to be rotating in the same direction, as if the entire universe has a preferred spin, Krint. According to some researchers, this unexpected finding contradicts our existing models and hints that our universe may have a preferred axis of alignment. If we were born inside a rotating black hole in a parent universe, that original spin would be baked into the very fabric of our space-time, giving the cosmos a built-in directionality that we are only just now beginning to map. This is what astronomers call cosmic anisotropy, the idea that the universe is not the same in all directions on a grand scale. It challenges one of the bedrock assumptions of modern cosmology, which is that the universe is uniform and homogeneous. And it is here that the theory adds its most sophisticated layer, the concept of torsion. In extensions of general relativity like Einstein-Cartan theory, space-time doesn't just curve, it twists. This twisting effect of space-time could generate a powerful repulsive force at extremely high densities, preventing a singularity from ever forming. Instead of a total collapse into a point of infinite density, the matter would experience a big bounce, a violent recoil that launches the birth of an entire new universe. It is a beautiful, self-replicating cycle of universes, and it even offers a biological explanation for why we are here to witness it. This model suggests a form of cosmic natural selection, where black holes that create stable universes with fine-tuned constants, like gravity and electromagnetism, are more likely to persist and reproduce. The universes with unstable physics simply vanish, while the ones that work, the ones like ours, continue the chain. It is a story that satisfies our deep need for order, meaning, and a sense of belonging to something larger than a cold, accidental explosion. But we have to be honest with ourselves. As seductive as the black hole universe is, we must treat it as a temptation, not a fact. It is a brilliant red herring that fills the gap between telescope data and human intuition. While it feels mathematically sophisticated, many mainstream astrophysicists suggest there are more pedestrian explanations for what we are seeing. Maybe our measurements of the Milky Way's rotation are slightly off. Maybe our instruments are playing tricks on us, or maybe our brightness to mass translations are simply naive. The danger of the seductive red herring is that it is so emotionally satisfying that it can stop us from doing the harder work of refining our actual reality. We love the idea of being broken because it makes the story more dramatic, but science often moves in smaller, more careful steps than a universe-shattering headline suggests. The mystery of MOM-Z14 and the impossible galaxies is real, and the tension in the standard model is undeniable. But whether we are living inside a black hole or simply misreading the first few pages of our own history, the universe is turning out to be far stranger than we ever imagined. As we move forward into the trial of the standard model, we have to decide, are we looking for the truth, or are we just looking for a more beautiful myth to hide in? As we stand before the collective body of scientific knowledge, it is time to convene the most significant legal proceeding in the history of astronomy, the trial of the standard model. In one corner, we have the prosecution, led by a faction of anomaly hunters and fueled by a global wave of sensational headlines claiming that our entire understanding of the cosmos is about to collapse. In the other corner stands the defense, composed of traditional lambda CDM, lambda cold dark matter, astronomers who argue that the universe isn't broken, but that our assembly manual for how galaxies are built was simply missing a few chapters. The star witness for the prosecution is a tiny glowing red smudge called MOM-Z14, a galaxy that sits at a redshift of 14.44 and is staring back at us from a time when the universe was only 280 million years old. The prosecution's opening argument is simple and devastating. The standard model predicted a quiet, dark nursery, yet James Webb found a neon-lit metropolis. They point to the fact that these early galaxies are not just present, they're extraordinarily luminous and appear to be over 100 times more common than the consensus pre-JWST models ever allowed. To the anomaly. Hunters, this isn't just a minor discrepancy, it is a cosmology collapse. They argue that finding a galaxy as chemically evolved and bright as MOM-C14 so soon after the Big Bang is like finding a skyscraper in a town that hasn't even finished laying its first roads. On social media and Reddit, this has mutated into the ultimate gotcha, the idea that the Big Bang itself might be wrong. But as the defense takes the stand, the tone of the trial shifts from sensationalism to scientific caution. The first thing the defense clarifies is a fundamental misunderstanding of the data. These galaxies are not dated independently and then found to be too old in a literal sense. Instead, astronomers use the redshift of the light to infer when in cosmic history we are seeing them. Therefore, the issue is not that the galaxies predate the Big Bang, but rather that they are far brighter, larger, and more structured than our simulations predicted. The defense argues that this is an astrophysics problem, not a cosmology collapse. They contend that the bedrock of the Big Bang, the expanding universe and the cosmic microwave background, remains unshaken, but our brightness-to-mass translations were undeniably naive. For decades, our supercomputer simulations were built on a set of assumptions derived from the middle-aged universe we see around us today. We assumed that star formation was a relatively slow and steady process, where only a small percentage of gas was converted into stars at any given time. The defense's key piece of evidence is that we underestimated how busy the early universe really was. They proposed that in the high-pressure, high-density environment of the cosmic dawn, the rules of star formation efficiency were radically different. Instead of the sluggish pace we see in the Milky Way today, early dark matter halos may have converted gas into stars with a violent, frantic efficiency that we never programmed into our models. This is the rapid early starburst theory, and it turns the prosecution's impossible evidence into a logical outcome of a more active universe. If these early galaxies were burstier, meaning they formed stars in intense, short-lived pulses rather than a slow crawl, they would appear incredibly bright to Webb's infrared eyes without actually needing to be too old. The prosecution counters by pointing to the chemical signatures. If the universe is so young, how can MOM-C14 already be rich in nitrogen and oxygen? The defense responds with the top-heavy IMF, the monsters of the first fire we discussed earlier. They argue that we were naive to think the first stars were like our sun. If the first stars were monstrous and lived for only a few million years, they could have polluted the universe with heavy elements in a fraction of the time we originally estimated. The tension in the courtroom reaches a fever pitch when the prosecution brings up the sheer abundance of these objects. They aren't cosmic unicorns as we once thought. They're popping up everywhere in Webb's deep sky surveys. To the anomaly hunters, this abundance suggests that the effective age of the universe might need to be reconsidered, perhaps hinting at a big bounce or a pre-existing structure that survived from a parent universe. They argue that the standard model is a house of cards and MOM-Z14 is the card that makes the whole thing tumble. However, the defense stands firm, characterizing this as a failure of imagination, not a failure of reality. They suggest that instead of rewriting the laws of physics or declaring the Big Bang dead, we simply need to update our software. They argue that we were SED naive, meaning our assumptions about how a galaxy's light, its spectral energy distribution, translates into its physical mass, were calibrated for a universe that had already cooled down. In the hot, early universe, a small amount of mass could produce a staggering amount of light, making these galaxies look like adolescents when they are actually just very energetic toddlers. The verdict of this trial is not a simple guilty or not guilty. Instead, the jury of the global scientific community is moving toward a nuanced middle ground. The Big Bang is not broken, but the history of galaxy assembly is being rewritten in real time. Webb did not destroy cosmology. It exposed that the early universe was much busier, faster, and more creative than our most advanced simulations ever dared to imagine. We are learning that structure didn't emerge slowly from the dark. It exploded into existence. The trial of the Standard Model reminds us that science is not a static list of facts, but a living, breathing process of constant reversal and refinement. MOM-C14 is a clue, a piece of evidence that tells us the story of our origins is far more dramatic than the slow and steady versions we've been told for generations. As we move out of the courtroom and back to the telescopes, the question is no longer, how can this galaxy exist, but rather, what else were we too naive to see? Because as we look deeper into the abyss, the impossible is becoming the new baseline for reality. While astronomers were busy debating nitrogen ratios and star formation efficiency in the quiet corridors of research institutes, something far more volatile was happening in the digital world. This is the story of the information mutation, the strange high-speed journey of a discovery from a cautious PDF on a server to a universe-shattering viral post on your phone. To understand the mystery of MOM-C14, we have to look at the second most powerful engine in the known world. Not a supermassive black hole, but the human desire for a gotcha moment that breaks reality. The mutation begins in a small office at MIT or UC Santa Cruz. A scientist stares at a monitor, looking at a little red dot, a compact high redshift object that shouldn't be that bright. They write a paper, choosing their words with the precision of a surgeon. They use phrases like astrophysics under stress, unexpectedly luminous, or tensions in the Standard Model. They title it something technical, like a cosmic miracle, a remarkably luminous galaxy at redshift 14.44. They upload this preprint to a server called Archive, a digital waiting room where other scientists can check their math. At this stage, the discovery is a question mark, a quiet invitation to look closer at the data. But then, the information leaves the lab. The first mutation occurs when a science journalist or a university press officer sees the preprint. They need a hook. A remarkably luminous galaxy becomes the galaxy that shouldn't exist. This is where the phrase first enters the public bloodstream. They take the genuine skepticism of researchers like Kevin Heinlein, who admitted his first reaction to JADES-GS-Z14-0 was that the telescope had simply fooled us, and they frame it as a crisis. The narrative shift is subtle but profound. What the scientists see as science working exactly as it should, by finding new data to refine our models. The headline frames as a failure of the model itself. As the headline hits the main news cycle, the second mutation happens on platforms like Reddit. Here the discourse splits into 3 distinct tribes, each carving out a different version of reality. The first tribe is the careful explainers. These are the users in r/cosmology who provide the highest signal in the noise. They patiently explain that these galaxies are not older than the universe. They're just too mature for our current simulations. They try to preserve the distinction between an astrophysics problem and a cosmology collapse, but they are often drowned out by the second tribe, the dramatic speculators. To this group, the little red dot is a weapon. They argue that if MOM-Z14 is this chemically evolved at just 280 million years, then dark matter is a myth. The Big Bang was a mistake, and the standard lambda CDM model is a house of cards. They aren't interested in refining the simulation. They want to see the whole theatre burn down. And then there is the third tribe, the full-blown myth makers. This is where the law becomes truly wild. They take the little red dot and fuse it with papers on cosmic anisotropy and the preferred axis of galactic spin. They don't just want a new model, they want a new myth. This is where Schwarzschild cosmology, the idea that we live inside a black hole, graduates from a fringe mathematical curiosity to a viral truth. By the time the discovery reaches Facebook, the third and final mutation is complete. The nuance of the little red dot has been entirely erased. A viral post, shared tens of thousands of times, takes the image of MOM-Z14 and attaches it to a headline in all caps. The Big Bang is dead. It claims that James Webb has broken physics and that we are all living inside a black hole baby universe. It merges 3 different papers from 3 different years into one sweeping mega mystery. The audience doesn't separate the subfields. They fuse every "Webb found something weird" headline into a single cinematic narrative of scientific collapse. This is the real mystery of the impossible galaxy story. Why are we so eager to destroy cosmology every time a telescope finds a new data point? Why does the idea that everything we knew was wrong have such high retention? The answer lies in our relationship with the vacuum of certainty. When the data outruns our intuition, when a galaxy like MOM-Z14 shows up with oxygen in its lungs and no black hole in its heart, it creates a gap in our story of the universe. And as humans, we hate gaps. We are a narrative species. We would rather have a radical, universe-shattering explanation than a quiet, we need to update our star formation simulations. There is something deeply seductive about being the generation that broke the universe. It makes us feel special, as if we are living at the climax of a cosmic movie. If the Big Bang is wrong, then we aren't just small observers on a pale blue dot. We are the ones who finally saw through the illusion. We reach for folkloric escalations, like black hole universes or higher dimensional mirrors, because they provide a sense of frontier wonder that a refined mathematical model simply can't match. We treat these discoveries like a detective pivot. We want the suspect to be something grander than just naive brightness to mass translations. We want the suspect to be the very nature of space and time itself. The information mutation reveals that our thirst for mystery is often stronger than our thirst for the truth. We turn science working as it should into a narrative of scientific failure, because the failure is more exciting. But as the little red dot continues to pop up across Webb's deep sky surveys, we have to recognize the mutation for what it is. The real drama isn't a single gotcha discovery. It is the collision between the absolute precision of a $10 billion telescope and the absolute chaos of how humans handle the vacuum of certainty. MOM-Z14 is not a reason to abandon our history. It is a reason to expand it. The fact that the early universe looks nothing like what we predicted is a gift, not a crisis. It means the beginning is alive, contested, and narratively enormous. But as the headlines continue to mutate, we have to ask ourselves, are we looking at the stars, or are we just looking for a reason to throw away the map? Because as we move toward the final frontier of visible time, the story we tell about the universe says just as much about us as it does about the galaxies at the edge of the abyss. We are the architects of the myth, and the mother of miracles is just the latest mirror we found in the dark. We are standing at the edge of what astronomers call the abyss of visible time, a frontier where the history of our universe stops being a matter of textbook fact and starts becoming a realm of cosmic wonder, and for some, a kind of cosmic horror. For decades, we believed the story of our beginning was a slow, graceful awakening from a dark, silent nursery. But as we push the James Webb Space Telescope to its absolute limits, peaking at a universe just 280 million years after the Big Bang, we are finding that the darkness was never empty and the silence was a lie. We have reached the moment where physics stops being merely history and begins to feel like a myth we are writing in real time. This is the true weight of a discovery like MOM-Z14. It is not just a record-breaking smudge of light. It is a step into an abyss that the human eye was never meant to see. At a redshift of 14.44, we are witnessing a galaxy that existed when the universe was barely 2% of its current age. If the cosmos were a single calendar year, we are staring at January 7th, a time so early that every single photon we capture feels like a stolen secret. The horror of this frontier is the realization that our comfortable stories about gradual growth and slow chemical enrichment are failing us. We expected to find babies, primitive, bare-bones collections of hydrogen, but instead we are staring at adolescents with the chemical ash of oxygen and nitrogen already in their lungs. The abyss is looking back at us with a maturity that defies our understanding of time itself. For the last few years, every time Webb spotted one of these impossible galaxies, we treated them like cosmic unicorns. Rare, beautiful anomalies that surely wouldn't represent the rest of the herd. We called JADES-GS-Z14 a miracle, and then MOM-Z14 arrived to snatch the crown, pushing us even deeper into the dawn. But the era of the unicorn is ending. These compact, blazing, red-shifted objects, often called little red dots, are not rare. They are popping up across every deep sky survey Webb performs. We are realizing that MOM-Z14 is not an exception. It is the herald of a new census of reality. The next step into this abyss will not be taken by Webb alone. Later this decade, the Nancy Grace Roman Space Telescope will join the hunt, and its mission will be to turn these miracles into statistics. While Webb is a deep dive machine, peering through a cosmic needle at a tiny patch of space, Roman is a wide-angle surveyor. It will scan huge swathes of the sky with the same ultra-sharp detail, hunting for hundreds, perhaps thousands, of galaxies like MOM-Z14. Every one of those will be a time capsule from an era we are only beginning to comprehend. When Roman's data begins to flood our systems, the impossible galaxies will no longer be shocking headlines. They will be the foundation of a new map of the early universe. We are moving from a period of astrophysics under stress to a period of total reconstruction. As this happens, the information mutation we see online, the viral claims that the Big Bang is dead or that we live inside a black hole, will likely only intensify. It is human nature to want a universe-shattering headline, to want to believe that everything we knew was wrong. But as we've seen throughout this journey, the real story is subtler and far more interesting. The Big Bang isn't a broken theory, and our telescopes haven't fooled us. We are simply witnessing science working exactly as it should, hitting a regime where our previous stories become fragile and our simulations are exposed as naive. We used to think the cosmic dawn was a slow, gentle sunrise. Webb has shown us that it was a flash fire. We are learning that the early universe was much busier, faster, and more creative than we ever dared to imagine. It was a place where monsters of the first fire lived and died in a heartbeat to seed the void with oxygen, and where gravity pulled matter together with a frantic efficiency that ignores our modern, slower models. This is the most satisfying closing note we can take. Webb did not break the universe. It did something much better. It made the beginning of time alive and contested. It took the first 300 million years of history and turned them into a battlefield of ideas, where dark matter, star formation, and even the nature of space-time itself are being re-examined with every new data drop. The impossible galaxies are not a crisis, they are a gift. They are the missing pieces of a cosmic puzzle that is much grander and more complex than we were once told. As we look toward the future, toward the launch of the Nancy Grace Roman Telescope, and the next decade of discovery, we must accept that the abyss of visible time will only get deeper. The record for the farthest galaxy will fall again. It's not a question of if, but when. And with each new record, our long-standing assumptions will continue to be chiseled away. We're no longer just looking at baby pictures. We're conducting an archaeological dig into the foundation of existence. The mother of miracles and her sisters have proven that the universe was born running. They have shown us that the fossils in our own backyard are mirrors of the farthest reaches of space-time. They have invited us to consider radical new ideas, from the seductive temptation of black hole cosmology to the rapid starburst efficiency of the dawn. And while we may not have all the answers yet, we have something better. We have a universe that refuses to be boring. Webb has opened a door that can never be closed. It has forced us to confront the fact that we are part of a story that is far more energetic and chemically rich than we ever imagined. We are the descendants of those first monstrous fires, and the heavy elements in our own bodies were forged in the very same adolescent galaxies that are now troubling astronomers 13.5 billion light-years away. The abyss is not a place of horror, but a place of homecoming. We are finally seeing the moment the universe first became legible, and in that light we are seeing ourselves. The trial of the standard model continues, the census of the unicorns is beginning, and the dawn is finally, truly here.